Hello and welcome to the 6th and 7th theorems I will be covering in these videos. There are many properties of lines and angles within a circle. The New South Wales syllabus for Extension 1 Mathematics mentions up to 16 theorems to memorise. However, some of these are the converse of others, which means it almost cuts it down in half. So far you haven't been expected to remember any of the proofs given. However, from now on, 3-unit students will be expected to prove any of the theorems in this video and subsequent videos. So let's get into them. This video is about Theorem 6, which states that the perpendicular from the center of a circle to a chord bisects the chord. This means if we have a chord and we draw a line that meets the chord at right angles, the chord will be cut in half. Here's the proof. We want to prove that the perpendicular cuts the chord in half. That means that AC is equal to BC. We know that AB is a chord and C is a point such that OC is perpendicular to AB. We have two triangles here, so we will be using congruence to prove it. In triangle AOC and triangle BOC, we know that AO equals BO because of equal radii. OC is common to both triangles, so they have to be equal to each other. We also know that angle OCA equals OCB because OC is perpendicular to AB from our data. So we have proven that triangle AOC is congruent to triangle BOC because of right angle, hypotenuse, side. Therefore, AC equals BC because matching sides in congruent triangles are equal. We have now seen that if we draw a line perpendicular to a chord from the center, it will cut the midpoint of the chord. The next theorem is the converse of the sixth. Remember, converse just means the reverse of the statement. And that is that the line from the center to the midpoint, so we know we're drawing a line that cuts a chord in half, will be perpendicular to that chord. So if we draw this line that cuts a chord in half from the center, it'll be at right angles, and it has to be that. To do this, we have to prove that the angles where the chord and the line from the center meet are right angles. So our aim is to prove that OM is perpendicular to KL, and we're going to do that by showing that OMK and OML are exactly the same and they're 90 degrees. We know that KL is a chord and M is a midpoint of KL. Again, we're going to prove this aim through congruence. In triangle KOM and triangle LOM, OK is equal to OL because of equal radii. This reason comes up a lot, so it's important to keep in the back of your mind. OM is still common, and this time we know that KM is equal to LM because M is the midpoint of KL. So triangle KOM is congruent to triangle LOM because of side, side, side. So now we can say that two angles, KMO and LMO, are equal because matching angles in congruent triangles are equal. Now we haven't proved our aim yet. Yeah, we know they're equal, but that doesn't mean that they're right angles. So what we have to say now is that KML is a straight line. Therefore, angles KMO and LMO have to be equal to 180 because straight lines add to 180 degrees. Therefore, because they're equal from our proof, they have to both be 90 degrees. So now we've proved our aim, that OM is perpendicular to KL. We will now look at two examples that use these properties. Example 4 says that PQ is a chord with a center of O. We know that PQ is 42 and OP is 29. We are going to calculate the distance PQ from O and give reasons why we'll do it. It's important to note at this point that the shortest distance from any point to a line is a perpendicular line. And we know that if we draw a perpendicular line from the center to a chord, then it will cut it in half. That was theorem 6 and 7. At this point, you should pause the video and see what you can come up with by yourself giving reasons. We're going to begin by calling M the midpoint of PQ, such that OM is perpendicular to PQ. Now we know that PM equals MQ because the line from the center of a circle perpendicular to the chord will bisect the chord. Therefore, PM is 21 millimeters because this is half of PQ, which is 42. Now we're going to use Pythagoras' theorem to find the shorter side of the triangle OMP. We should know that OM squared equals 29 squared minus 21 squared because of Pythagoras' theorem, and I'll use that reason in brackets. So OM squared is 400, and therefore OM is 20 millimeters. We can now say that therefore the chord PQ is 20 millimeters from the center O. You should always phrase your answer in such a way that it specifically answers the question that is being asked. Our second example looks different to the last, just demonstrating the varied problems you can be given in this course. The question says that O is the center of the circle ACB, and that P and Q are midpoints of AB and BC respectively. We are asked to prove that angle POQ plus angle ABC is equal to 180 degrees. At this point you should pause the video and try the question for yourself. A hint would be to use the theorems you have just learned and use the fact that POQB is a quadrilateral, whose angle sum is 360 degrees. Okay, we will begin by stating that OP is perpendicular to AB because P is the midpoint of AB. Therefore, angle OPB is 90 degrees. We also know that OQ is perpendicular to BC because Q is the midpoint of BC. Therefore, angle OQB is also 90 degrees. So those two angles, OPB and OQB, add up to 180 degrees. But all four of those angles, including the ones we want to prove add to 180, have to add to 360 because the angle sum of a quadrilateral is 360 degrees. So we have proved the first two angles add to 180 degrees, and if we subtract those angles, we are left with angle POQ plus angle ABC equaling 180 degrees. The next video in the series covers chord properties 8 and 9 and looks at the distance between two chords of equal length and the center of the circle. Thanks for watching.